distribution of galaxies, but on a galaxy scale, it's essentially irrelevant. Maybe you can stand up and shout.
All right. So my question is, how do supermassive black hole form, and when do they form? Because I saw your slide that they form in very high shift, but do we have any evidence that we are seeing the formation of supermassive black holes?
So we haven't seen them yet at the highest redshift. This is again one of the goals of a next generation of large telescopes. You potentially can discover small quasars beyond redshift 7, 8, 9, 10, whenever reionization happened, around 15, something like that, okay? But as I try to emphasize, I see them here. So even though these are local objects, this is not a high redshift. The fact is that these are small galaxies. This is how likely galaxies were when they at very high redshift, and these are very small black holes. And from what we can tell, what I did not say is that even though these galaxies lack a bulge, what they always have is a very dense central nucleus or concentration of stars that we astronomers call a nucleus star cluster. Okay, so there's a central concentration of stars, and these small black holes, 10 to the 6, 10 to the 5 solar mass black holes, invariably live in the middle of such a cluster. So it appears that that's an environment that's helpful to produce these things, and there are good theories of how that can happen. Basically, one idea that's very plausible is that you can form these 10 to the 5 solar mass black holes, but once you have runaway growth of a few compact remnants. Okay, so in a dense star cluster, if the massive stars can sink to the center of the cluster by dynamical friction before they blow up, supernovae, okay, they'll produce stellar mass black holes, okay, with masses of say 10, 20, maybe 50 solar masses. Okay, we know that nature can make those things, and if you have just a couple of these, you can have runaway coalescence. So there's simulations that have shown that that's a plausible way to grow such a thing. Okay, so I think that's a very good bet. It doesn't mean this is the only channel. Maybe what people say at high redshift is true, that you can form it through collapsing, pristine clouds. But this is what we can see. So that's a good start.
Well, so the scaling relation should imply some underlying physics, right? So there has to be a reason why they scale. So for example, you can say the bulge is a reservoir of mass which somehow has some dissipation and allows you to gather the mass in the center, right? So therefore the scaling down to smaller and smaller mass where you don't see the bulge, is that just the terminology is wrong, calling what you call bulge? Or is it just that the fact that you have a small nuclear cluster that's also providing that mass, right? So if you calculate the mass of the nuclear cluster, does it fall on the line?
Yes, it does.
Okay.
Yes, it does.
So is that the underlying physics?
Apparently, but exactly what is the physics, I think I would say is now up in the air, because the physics apparently is due to, again, this energy coupling. Okay, so the bulge, the cluster, has gas, which can do two things. It can form stars, and they can accrete and grow the black hole, and they self-regulate each other, apparently, according to those movies. Okay, in such a way to preserve this type of scaling. Okay? That's what they say. But what I've also shown you is that can't really be, that apparently really isn't the story. Because if you go to the highest redshift quasar, if this happened, then it happened then. Okay, I don't see that. Okay, right? The galaxies, the submillimeter galaxies, which are the galaxies that are young, that are undergoing this process, they've already formed all of their stars, and most of their stars, but their black holes lagging behind by a lot. Okay,
Yeah,
so
would that be a time problem?
sure. but that's not seen in these models. Okay, so there's something is not quite right. I'm sure they can go back and tweak things and explain it away. Okay, but on the surface of it, at least the models, the ideas that people have put forth, don't predict that. On the other hand, there has to be some regulating mechanism. As I've told you, how do the black holes know to grow, you know, to reach this upper ceiling? You know, why does it overshoot? Why does it undershoot? Okay, so apparently there is some boundary that it cannot go beyond. So there is still some internal regulating mechanism, but it's not this tightly synchronized way that is often talked about. Okay? And you know, that's for the theorists to worry about. But I think they need to go back to the drawing board on this. Yes.
So you mentioned that the M sigma relation has a dependence on the redshift. So does the intrinsic scattering of the M sigma relation also have the dependence on the redshift, or has the dependence on the bulge mass?
That's an excellent question. Okay, I don't dare say anything about that because, as I mentioned, sorry, I'm going. Okay, never mind. For the high redshift stuff, you see we're using different methods to estimate the mass of the black hole. So for high redshift objects, we have to rely on these quasars, these indirect methods, okay, where it's just intrinsically just much more uncertain. Okay? And also the information we have in the host galaxy is also much poorer. We have this bright quasar shining. We're trying to dig out, you know, the galaxy underneath. Okay, so there's a huge observational and I would say almost unquantified uncertainty, you know, on both of these parameters at the moment. Okay, so I think this is too early to say, but things are going to get a lot better. So for example, a lot of the host galaxy stuff, for example, came from EVLA and ERAM observations and early observations of ALMA of C+ and CO lines. Okay, which is just integrated line emission. So you measure some line width, basically. Okay, you're basically measuring the Tully-Fisher relation. For those of you know what I'm talking about. Okay, we have no idea what is the inclination angle. We have no idea what is the size scale. So it's just some statistical average. Okay, but as ALMA gets better and better with better resolution, we'll resolve it. Okay, in fact, some of them have the gravitational lenses have been resolved. Okay, so we're almost there. Okay. And when the GMT and TMT come online, okay, we're going to have a factor of 10 higher resolution HST. In fact, then we can do away with the quasar. We can directly detect massive black holes with 10 to the 9, 10 to the 10 solar masses at any redshift. At any redshift, okay, because of the angular size redshift dependence. Beyond redshift 1.5, it doesn't matter. Okay. So the diffraction limit is what, you know, 1/10 of the HST. Okay, so we can directly do what we do at redshift 0. You know, of course, it's still going to be sensitivity limited. It's not, you know, infinitely large aperture. Okay, but so we can begin to do that kind of stuff for real. I would say, you know, a few years time. I mean, ALMA, I think in a few years time. GMT in about 10 years. TMT in 10 years time. So I think the intrinsic scatter is too difficult a question. I was just glad to see anything. So the fact is that there is a relation, right? I did not expect that at all.
Okay, the last question.
Yes, you updated black hole mass bulge issues at 0.5%. However, as you mentioned about the Coma-Crust ultramassive black hole, essentially the fraction is much higher. For example, like MGC 1277 is 1%. So I'm wondering that in the future, hunting the ultramassive black hole maybe increase some fraction. Do you have any idea, suggestion?
That could be the case. Okay, so what Nakamura-san is saying is that there is one object called NGC 1277 in the Perseus cluster that has a black hole mass to bulge mass ratio, which is a factor 100 higher. So there's a huge outlier. Okay, it's a big black hole. Okay, almost 17 billion solar masses that has a very undermassive galaxy. So I think there is such a population of outliers. We haven't found many. Okay, that's one. Okay, there are a couple others less extreme, and those are interesting. In fact, they may be the survivors of the high redshift quasars. Remember, the high redshift quasars are way above, and it's possible some of them stayed that way. Again, because whatever merger tree that galaxy had just missed its chance to grow. Okay, so you know, so it's again, I just find it fascinating that we can find these things. To generalize them to say, you know, what the statistics are is really too premature. But it's enough to just find them. It's fascinating. Yeah.
Okay, so Professor Hong will be our institute today and tomorrow. So if you have more questions, you are always welcome to look for him. So let's thank our speaker again.